which it's a network, international network based out of Australia. And our exhibition, this is the second version of it, and we're happy to have it here in the library through May. And we have over 25 researchers, international female researchers in robotics and female-led teams of robotics from over 8 different countries. So it's quite a wide range. There's a bit of an architectural bent to it, but also very much artistic and performative. So we'll actually get a chance to go peruse the exhibition and socialize it at the reception, because we'll adjourn over there after we're done here today. It's also a bit of a special celebration because part of the SHErobots network and mission is actually about this lineage of female researchers in science, and specifically in robotics. And our 2 speakers today actually have this relationship and this lineage too, because one of them has taught the other one here at the TU Delft. So this is quite a nice relationship that has been fostered, and we get to see come to fruition, as now they are also a professor here. So this is quite a good thing to enjoy and for the community and of researchers, and also trying to make sure that we have, let's say, getting to a little bit more of an equilibrium in terms of female faculty in the sciences as opposed to the male researchers. So I'm not going to introduce too much more about the program and the exhibition. We'll see that, but the concept for the side program of this exhibition is to then extend this network to the TU Delft. And so we're putting pairs of faculty members, female researchers in robotics, in conversation with each other. They're highlighting their research, and we'll have a little bit of a discussion about gender and its role in research, and also the theme of the exhibition, which is ecologies of care. And then we'll open up to the Q&A. We were scheduled to have a demo this evening, but unfortunately the robot was double booked, so the robot itself couldn't come out, and so we have lots of videos to update you, and we have a nice prototype to share with you, and the bases will be covered, so you do not have to worry. We'll get plenty of good robotics action in the presentations. And with that, I will formally introduce the speakers. Our first speaker will be Henriette Bier, who is the initiator and leader of the Robotic Building Lab, Associate Professor of Architecture at TU Delft, Honorary Associate Professor at University of Sydney, and co-founding member of the TU Delft Robotics Institute, and the International Network of Adaptive Environments. Results of her research have been published and presented in more than 200 journals, books, and exhibits. And our second researcher presenting today, Mariana Popescu, Assistant Professor of Parametric Structural Design and Digital Fabrication in the Faculty of Civil Engineering and Geosciences, is a computational architect and structural designer with a strong interest in innovative ways of approaching the fabrication process and use of materials in construction. Her area of expertise is computational and parametric design with a focus on digital fabrication and sustainable design. All right, let the conversation on robotic building begin.
Thank you, Vincent. I think it's a little bit too loud. Maybe now it's better. For inviting us to celebrate with you all the International Women's Day. And as you mentioned also, for me, the beauty of this moment is also that my former student, Mariana Popescu, is going to present her work. Former student and currently colleague. And it's nice also to see some of my former students here, and also my current students. And I hope that this is going to be inspiring for you all. And I'm going to present It's not working? Maybe this way? This way? It worked before, but... Yes, okay. So let me just try now. Yes, it works. So I'm going to present the work that we have been developing in the Robotic Building Lab since 2014, when we established the lab. And we are working with a group of master students and PhD students on projects that focus on developing robotic systems that are integrated into the physically built environment and also in building processes. How do we do that? We develop design to robotic production, assembly, and operation methods, which I'm going to explain in the following slides. So we started by connecting a robotic arm with the computational models that we developed in Rhino and Grasshopper. And we developed also an end effector for 3D printing. So the first exercise in 3D printing was implemented using ceramic clay. The researchers involved at the time in this project are at the moment at ETH Zurich, both doing their postdoctoral research there. And at the time, we developed this technology and we tested it. As you can see, we start with an overall design. In this case, it was a pavilion. And then we translated the computational model, the geometry, into physical paths, robotic paths, using, in this case, light. And we also tested the 3D printing on various backgrounds. In this case, it is a double curved surface. But usually what we do, also in this case, we followed the same principle. We selected a fragment of the pavilion, as you can see here. We structurally optimized it and created a Voronoi-based pattern. Here you see a drawing experiment with this first pattern. You see that the cells, Voronoi-based cells, are at the moment drawn separately, while when you 3D print, you want to have a continuous path. So this was the next step, creating this continuous path and 3D printing one-to-one prototype. So this was basically the first experiment that we implemented in 3D printing, robotic 3D printing. And here you see the optimization routine that we implemented. So why do we use this material design? We use this material design because it reduces material use and also 3D printing time. But also at the time we were speculating that probably it increases insulation properties. But we didn't know if that's correct. So later on, we indeed also tested it. But I'm going to get back to that as soon as we get to the project where we did that. So this Voronoi-based material design is very versatile. So in this case, we 3D printed with thermoplastic elastomer in collaboration with an industrial partner in Rotterdam. And we 3D printed a chaise longue with variable stiffness. What does it mean? The back of the chaise longue leans back when the user is leaning back. And again, we implemented the structural optimization and also the material design in such a way that the higher density parts are stiffer than the other ones. Here you see the system that we used from 3D robot printing in Rotterdam. And I think I'm going to go there because the sun is blinding me. And again, we usually use rhino grasshopper to develop the design. And here you see the cellular design that we then tested, first on fragments, and at the end we 3D printed the whole chaise longue. So the logic is quite clear. Higher densities means it's stiffer. And here you see the 3D printing process. It took about 30 hours in one go. Here you see the researcher, very dedicated one. He spent basically the 30 hours next to the system, and 30 hours including troubleshooting were implemented. And here you see the variable stiffness. So continuing basically on this line of thought, structurally optimizing, 3D printing certain parts, but also having, let's say, subtractive, not only additive, but also subtractive techniques implemented. We developed a project where we worked with curvilinear beams consisting of recycled wood, and we 3D printed the nodes, optimized and 3D printed the nodes. So here you see the overall design, which is an atrium in an existing building. And you see here the structural optimization routine. The beams change, so to say, thickness according to that. And then again, we take a fragment and we develop also the optimized nodes. And these optimized nodes are 3D printed with technology developed here at mechanical engineering. So this is still work in progress, but in principle, the technology is, as mentioned before, available here at mechanical engineering. So again, how we did it, we took recycled wood, we glued it together, and then we milled these curvilinear pieces of wood. Again, it's a fragment, but it has been quite impressive to see that the various pieces of wood and the different colors and patterns have an aesthetic quality, I would say. So what we identified, of course, was that we created a lot of sawdust. So then the question was, okay, if we want to have a complete circular loop, we need to use the sawdust. And then we developed a project, is actually this one here, planetoid. We call it planetoid because it's a small planetoid that is 3D printed from wood, a combination of wood and thermoplastic elastomer. And this project, as mentioned before, was implemented with a landscape architect. And the idea was that this cavernous structure is harboring not only animals and insects, but also a ball of earth from which plants can grow. And these planetoids would be distributed in leftover spaces in the city, similar to this image here. And as you saw, there was actually an insect already just after we 3D printed crawling on top of it. And these cavernous structures also harbor sensors in order to monitor the climate, indoor climate. And this indoor climate data is available on a website or an app. And the idea was that the neighbors and passers-by are encouraged to care for these plants. So for instance, they would be notified that the plants are too dry, they need perhaps more water. So with this, the hope was basically that the users are going to engage in a caring manner with these locations. And one of the challenges, of course, for when it comes to 3D printing is the componential logic, because in principle you can print only parts. The size depends a lot on the robotic system that you have. So the componential logic in this case involved consideration with respect to how the parts are not only 3D printed, but assembled together. Master students actually explored scaling up this approach. They proposed a larger scale urban furniture based on the same principles, where the human would also be part of this environment. So basically the idea is to share these environments with animals and insects and humans. So moving towards scaling up, 2020 we have received funding from the European Space Agency to develop a Martian habitat. So this was again a bottom-up project because the students, they wanted to participate in this idea competition, and I didn't feel quite comfortable because I was thinking, well, there are enough challenges of building on Earth, going on Mars. We don't know a lot about Mars. We know some things, but a lot we don't. But European Space Agency said, okay, go for it. So we ended up indeed developing the idea. Students explored the possibility of using this Voronoi-based design to facilitate various functionalities. And as previously shown, we worked again with this Voronoi logic, the structural optimization, then developing the point clouds and controlling the Voronoi based on this point cloud. So in this case, we also did a light analysis and developed a system with integrated AI, where the lights would, for instance, in this case, follow the moving of the human in space, or would change color and intensity depending on the activities that are implemented. Again, we focused on a fragment, on a component, and this was basically the first test we implemented with the system that was developed by Vertico in Eindhoven. So they are 3D printing large-scale structures, and we used the material that they had, which is a cement-based concrete. And you can see the difference between the computational model and the 3D printed prototype. So this is a very important step, the prototyping at one-to-one scale, because you need to establish a feedback loop between the design and actual prototyping. This is the 3D printing implemented at Vertico. And this is now the 3D printing using regolith simulant. So regolith is the material that you find on Mars. And we tested, so one of the tasks was, does this work? Can we 3D print with regolith simulant? And what are the qualities of this material? But before going into details in terms of the material properties, I would like to focus on again on the componential logic, because at the moment we are looking, of course, at large-scale structures. So this is maybe, the planetoid is maybe more easy to produce, but this is basically a habitat. And we work together with mechanical engineering, the cognitive robotics lab. Luca Peternelli in particular was leading this work package. And here you see the human-robot interaction approach. Is guiding the hand. This is a master student, to grab the component.
Close hand.
And it gives basically commands, like close hand, lift up.
Orientation. Main mode.
So basically, in this mode, for instance, is compliant. So the robotic arm is doing what the human wants. Now it's directed by the robotic arm.
Down.
Yes. So there are moments where they work together, but there are also moments where the robotic arm is doing what automatically is taught to do. So this was basically a first assembly of two components. So we started with pick and place, and then we continued with the assembly of two components. This was implemented with Master 2 students, again at the Cognitive Robotics lab. And we implemented the computer vision, so object recognition using computer vision. And as you can see, with computer vision, we can detect the objects, although they have a complex geometry. And we can detect also the grabbing holes for the robotic arm, so that the robotic arm recognizes where they are and where to grab. Here you see the simulation of the process on the one hand side, and then the implementation. So in this case, the components were assembled vertically next to each other. This semester, with the Masters 2 students, we are developing an assembly that is horizontal. We expect that at the end of the study, we are going to have an approach for for assembling a whole building. So, and the assembly is implemented with Zebro. This is actually a rover developed by TU Delft. These are the smaller versions. Of course, in our case, the Zebro would be larger, so that we can mount a robotic arm on it. And also, the various Zebros are equipped to handle different activities. So, but this is still a work in progress. The plan is actually in May to go with a Zebra rover to a cave in Sicily. It's a collaboration with University of Palermo, to scan a fragment of the lava tube, and then use basically this as basis for developing further the design. So here's an impression of the interior of such a structure, developed again by a master's student. And the idea was to look into the distribution of plants for an indoor garden, and also to have lighting that is integrated. And we are going to use a technology that we developed already a while ago, and it was tested here in a prototype. So the integrated light would change color, would intensity, but would also turn on and off and we would be able to control this by monitoring the humans moving in space and learning. Basically, the system would learn from the humans to adapt in time. So this is actually the demo that we were planning to present here, and unfortunately we ended up not being able to present it, but I have a good documentation of it. So the planting of in the indoor garden of the habitat is going to be also implemented with a robotic arm. So again, we implemented object detection. In this case, these were bulbs, flower bulbs, and the robotic arm is on the one hand, it can create, so to say, the for some reason it's not working. Yes, so it's creating the holes, but also is able to pick and place the bulbs, and in some cases works together with the human for specific tasks implementation. And this project was implemented in collaboration with the University of Sydney. To continue basically this designed robotic assembly line of thought, I would like to present also this componential furniture reconfiguration that we developed actually for the library. And we intend to use the same principles also for the habitat on Mars. So these are porous, 3D printed, lightweight booths that can be taken away from the original location and moved freely in this space. And one of the challenges, and this is of course because the library wants to have opportunities for having various activities taking at the same place, taking place at the same time, as it happens also now. And you see basically that the students developed a larger structure that could accommodate a group of people, and the smaller booths can be moved. But one of the challenges is to be able to bring them back. So how do you find basically these booths and bring them back to where they belong? And for that, the students developed object recognition. You see there the individual booths are identified, and the idea was that basically you would have your phone with which you can identify the Voronoi and their Voronoi-based booths, and you could therefore bring them where they belong. So in case you are interested in these topics, I wanted to share, this is a book that I edited 2018, and this one previous year together with Philippe Morel. Definitely these technologies are extremely relevant, and we need to start to understand how to work with them, and also the students need to learn how to implement them, understand their meaning, and also their potential for architecture. Thank you for your attention. All right. Thank you. I'll see where I can stand so the sun doesn't blind me. It's a rare occasion that the sun blinds us in the Netherlands. It's very nice to be here, and such an honor to speak after Henriette, because
12 years ago or more, I would not have anticipated this, right? I was just graduating, so this is quite a special moment. In my presentation, which is entitled Digital Materials Across Scale, and I'll explain why, you'll see a lot fewer robotic arms. You'll see plenty of arms. They might be human arms, but it might be a little bit of a different definition of what robotic means than the usual one. And by that, I understand that it's any sort of CNC process, something that is steered by a machine and computationally done, could be interpreted as a robotic one. You'll see some robotic arms too, just in case you were thinking of standing up and leaving because we don't have it. So as an introduction, I wanted to say something about myself. So I'm somewhere at the intersection of architecture, structure, computation, and fabrication. Most of it as a result of my education, both at TU Delft and the heritage of having done a PhD with the Block Research Group. So I spend a lot of time trying to, as a result of that, trying to couple geometric form with material efficiency and how we might be able to make those forms, to realize those forms. That means that, and this is a little bit of an explanation of the title, so Digital Materials Across Scale. It means we deal with geometry a lot. Not only global geometry, so global geometry we might think of as an architectural form or a structurally informed geometry, which is our preference, as has been also outlined, because it gives us some louvers or some possibility to probably be more effective or efficient in our material use if we do that. And personally, not only personally, but again, a lot of us in the field believe that if we do have that coupling between geometry and structure and efficiency, we're also going to get pretty elegant, beautiful architectural forms. So it's a matter of taste there. But it's not only the global geometry, so we can talk about global geometry and material at that scale, but a lot of the work that I do also looks at local geometry, so actually looking at the material, zooming in, and trying to make this relationship across scales, right? So between the global and the local in those terms. I won't stay too long on that. Part of the motivation for looking into those are that the construction industry at the moment faces two main challenges. One being the environment, that everybody knows, because every industry faces the environment. And the other one is digitalization, as in we're not very productive and not very digital in general. And it's believed that, well, it's the hope that by addressing one of them, we might be able to have a positive impact on the other. That doesn't mean it's the only solution, and it doesn't mean it's the solution that will bring it about, but it's one of the tools that we have in our toolbox to go there, and it's my tool of choice at the moment. That means that we think usually in terms of how we might design, so that we hear that, right? We need to design differently, we need to construct differently or build differently. The invisible connection between those two is often left not specifically enunciated, and that's fabrication. I put it very boldly in the middle because I work a lot with fabrication, so that's kind of my point of focus in this case. It doesn't mean that they are separate. This is something that's interlinked, so one has an effect on the other. I won't very specifically talk about design, but you'll see how design comes back within it usually. The reason we might find it interesting to focus on these three things is because they give us an opportunity to be more effective with our material use, to tailor material properties, to reduce construction waste, so on and so forth. But the only way we can make that link between those two, so we can enable our designs, constructions, and fabrications to do that, is very critically through computational tools, or our little digital robots in this case. So a lot of my work also focuses on those computational tools. If we talk about construction, very briefly, just to put it in context, because I will dive very fast to concrete and how we might do something with concrete, I think about construction as in a lot of the buildings that we have around us. And if we want to be more efficient with our constructions and use less material, we usually can design better forms. That means that we can have very thin, elegant shapes that span large areas, and they don't use as much material as the ones that we usually construct. Unfortunately, that usually kicks the problem down the line to how we build them, because when it comes to building them, that becomes a little bit difficult. So we usually need clunky, difficult molds. And if we want to be a little bit more efficient, we can't just turn a blind eye, go to the next one and say, tomorrow's problem. So I look at the formwork side of things. To do that, most of the focus is on developing a lightweight fabric formwork, a flexible formwork, which is something a little bit different than the traditional formwork, because it's fast to produce. It could reduce waste, and because it is a flexible formwork that uses a textile, specifically a knitted textile, so I'm sure somebody in the audience will really enjoy this. It means that we could also use it with minimal intrusion. I really appreciate it, don't stop. Then how this would work really quickly is you start with a design, hopefully a structurally informed design, but whatever design that could work with a tensioned textile. We fabricate a textile that fits said design, then tension that textile in a rig, because it needs to get the shape somehow, and then apply a thin coating to get the formwork. Now, the thin coating, particularly for the moment, is crucial, because a knitted textile, is very soft. So if you can imagine trying to cast something heavy into it, it's going to deform quite a lot. That's not what we want to. That was not the point all along. So that building up of layers, of strength in layers, is what makes it possible to do this, which is why we need a coating. Now, there are two challenges to this. The first one is, if we have a design, how do we get to said knitted textile? That is a challenge on its own, and it's addressed through computational pipelines, right? We need to translate that. And the second challenge is, how do we get from, once we do have that textile, how do we actually build with it, right? So what I'll do is I'll give you a few examples of these two challenges. I'll start with the second one, so I'll show you how we build using a textile, and then come back to the computational pipelines. So the first example is a pavilion that we built in 2018 in Mexico City. It's called Knit Candela because it's an homage to the famous shell builder Felix Candela, and it's built close to one of his, as an homage to his Los Manteñales in Xochimilco big restaurant. So it's one of the shells that you've seen in the previous slides as well. The interesting part about this is that it's a thin concrete shell with rib stiffeners in two directions. So you'll see some cavities here. Why this is interesting is because usually when you have, when you need a formwork, that means we're dealing now with two complexities. We deal with the global geometry, so we need to have a globally doubly curved geometry, that's number one. And then we also deal with the local complexity of needing to have these little pockets of material saving in between it. So we're dealing both with the local and the global geometry in that sense. The way this was done is by knitting a textile for it. That's what the machine looks like. Because the structure is rather big, we need to segment that, right? So we don't have machines that are as big as our buildings. We did it in 4 pieces. You'll see us, me and Lex, that's my colleague, he's gonna come back later as a very apt robot. We put that into 4 bags, vacuum bags, and took it to Mexico in our suitcases. Sure, because it's easy to take it in a suitcase and make a point. Also because we finished quite close to the deadline, so sending it beforehand might have been a bit tougher than one thinks. On site, those 4 pieces are put together, so you'll see an entire piece over there. We ran cables through them, so steel cables in 2 directions to make a cable network. You'll see it in the next image quite fast. And what you see outside is the frame that was being built to tension the textile in. It looks a little bit like a mess still because it was under construction. Once tensioned with the cables, so you'll see cables running along in these directions, vertically and as loop cables around. Once tensioned, it looked something like this. This image I like a lot for 2 reasons. One, it shows the lightness of the system in the sense that not just because the light is shining through, but because if you were to imagine a doubly curved surface made out of foam or timber, in this case, it would be quite filled with supports and formwork inside. And the second, because we hadn't really built something that big with a knitted textile before, it meant it stretched to we didn't know for sure if it we had reason to believe that it would, but we didn't know for sure that it would stretch to that size. So this is a moment where you say, okay, good, it worked, so far, at least. Once tensioned, we filled up pockets that were put in the textile with balloons. Clown balloons, because we're funny sometimes, and we don't take ourselves too seriously all of the time. And started applying the specially designed cement paste coating. And I promised you would see Lex come back. So Lex was my colleague at the time, and he is the concrete magician, so the one that came up with the very special formulation for that cement paste coating so it would work in an outside environment. And you can see him applying that in a very automated manner from a scaffold. Once coated, it looks something like this. All of the ridges that you see in between those pockets become the ribs in the concrete, and then the rest, the concrete slab. With this, then concrete could be applied, and you'll see that this is done also in a very automated fashion, but using very skilled local craftspeople. And that's because we were in Mexico City, where there is a long-standing tradition of having good concrete workers in that sense. So they really know how to make this very, very beautifully. And although I don't have the next image, but you saw the first one, I would say that Felix Candelas probably would have been jealous of the finishing that they managed to give to the concrete. Once concrete is hardened, you can take the scaffolds or the supporting frame off, and you're left with a structure that has concrete on the outside and then the textile on the inside that's not removed. Some of the takeaways from this project are that for 50 square meters of formwork, that includes the textile, the cables, all the connectors for that, but not the timber frame. It cost around 2,250 euros. The textile weighed about 25 kilos, so it's really lightweight compared to any other type of formwork. The cables and so on were another 30 kilos, so 55 carried 5 tons of concrete in the end. It took about 36 hours of machining time, which is very funny because I heard you say 36 hours for the other one, so I was thinking, that's nice. Those are just coincidences, but 36 hours of machining time to get the textile out of the machine. And it took about 14 weeks between the start of us sitting together to talk about the project and the project standing there. Now, normally, if you were to make a milled foam formwork for 50 square meters, it would take about 720 hours, which is roughly 14 weeks. Now, this is a little bit, so it says something about the type of productivity that we can reach with such systems. But this is also a little bit cheeky, because 14 weeks doesn't take into account that there were 2 years of development before that. And 14 weeks also were not Monday to Friday, 9 to 5, so that's not a fair comparison to the 720 hours that are otherwise done this way. Nonetheless, it's still a great improvement in terms of productivity, and one that is not possible without having those computational tools to get you there, right? And this is where we get to the fabrication side of things, so the computational pipelines before, and that is, we have a machine and we need to instruct it. Usually these machines create things that are the size of ourselves. They create clothes or shoes, so they make parts that are about this big, meaning that the instructions at that scale are also easier to make. But if we want to move to a construction scale or something that is a bigger building, then we need to have pipelines that automatically translate a design into those patterns that can be fed to the machine. And without that, we wouldn't have that type of productivity. This is not only interesting for us, so here's my robot. That's not only interesting for us, it's also interesting for the machine manufacturers, because that means that it opens up an entire new sector for them, right? Whereas they were always in the fashion industry, now they might have a leg to stand on in the construction industry. It's going to take some time, but they might have one. And although we show the machines all the time as one, because we happen to have only one to make these projects with, the truth is these machines are there all over the world in factories, in huge factories, in large numbers. So if we know how to generate those instructions for them, we don't even need to take textiles in our suitcases or trucks or whatever else. We can just send the instructions and have them be produced rather locally. I took a little bit of time in explaining that project, but I wanted to show you a second one, which is an evolution of the first one, in terms of, well, both of scale and and you'll see how that comes back for the computational tools. We built this one in 2022. It's called Knit Nervi, and you see a pattern, knit everything. But Nervi, in this case, it's a homage to Pierluigi Nervi, and the structure that, that we echoed here is the Palazzetto dello Sport, which was about 200-300 meters away from where we built this structure. What you see here is, again, a type of structure, a shell structure that has a nice diagrid ribbing in two directions. And these types of things might be a little bit more complex to build just with standard repeating units. So what we wanted to do is, well, of course, we reimagined that geometry, but it works in the same way. And we wanted to also bring it a little bit closer to what industry might recognize as something that can be useful, right? If the first one, you might think, it's an artwork and it's a doubly curved shape in general. This one is trying to address industry a little bit closer. Doesn't mean it's completely close. But what you'll see is that we have prismatic sections that are recognizable with straight edges. And we've also introduced reinforcement, which you'll see inside a little bit in the rebars as this X-ray through that structure. What we also tried to do with it is reduce the amount of external support that you needed. So that wooden frame that we had before, that you would rightfully claim, yes, but that's a one-off waste. We agree. So how could we do that with even less external support? So it looks small because the pictures are either aerial or because it's in front of the Maxi Museum, which is huge and it dwarfs anything around it, but it's roughly twice the size of the previous structure that we've shown you, because it's 9 meters in diameter and it's about 120 square meters of textile, just to give you the range of it. In this case, what we set out to do is have the rebar cage as a bending active grid shell, be the part that stays within the structure theoretically and fulfills a structural role, but is also actually the scaffold to hold up the textile, so you don't need an external one. Then that internal scaffold holds up the textile, and we would cast only into the ribs of it. The only not used part of the scaffold are those props that you see over there, but those are standard formwork props, so they can be found with any contractor, and they can be given again for any other project. Now, what we did is we built first the bending active grid shell, so you'll see it here. We then created all the knitted pieces specifically for that structure. I'm bringing this image back again because I wanted to highlight that for this, it means that we need to have a better evolution of those computational tools, because we're making a bigger surface, so it takes a little bit more time. So we need to make sure that we scale up those systems with the scaling up of our structures so that they don't become a bottleneck. You'll see a little video that shows kind of a snippet of these types of patterns that are given for the machine, and you'll see that there are a lot more pieces. So the segmentation of the building, in this case, is a little bit different than the previous one. You'll see it working. So that's, again, the same type of machine, but this time at TU Delft. You'll see all the pieces that were being put together. And again, they fit in a bag. So we take it to site because we can still fly to Rome. And on site, you'll see that these types of systems are easy to assemble, sometimes by one unskilled laborer, very, very quickly. So in the end, it looked something like this, and you might note that we didn't cast any concrete into it. And the reason we didn't cast any concrete into it is twofold. One of them, well, we said we've shown that we can, so it's not necessarily the first thing that we need to show. Second, it was a temporary exhibition, meaning that it was going to be there for 5 months. So if we want to showcase a type of formwork that's very sustainable, perhaps casting something temporary in concrete is not the best way to go. That being said, it would have been nice to be able to really test it out and all of the way. So what we did instead is we made it fully disassemblable. So all of these pieces are not sewn together or something else. You can also take them apart. So at the end of the exhibition, this was disassembled. It has not been reassembled. The last thing that comes back to the materials across scale, and again to the computational tools, is if you look at the diagrid in between those beams, which was not meant to be cast with concrete for this, so it's actually not serving a structural purpose, you'll see that it's not a uniform material, right? It's something that is a graded material. It has different densities. And this was one of the, although in this case it's an aesthetic one, it's one of those parts that we needed to be able to show, both in terms of computational tools, that you can actually control that material placement at that level and control that within the fabrication process as well, not only within the design process. So finally, because I think I'm speaking way too long, so I want to stop, I wanted to show you what kind of brings these together, right? Because I've shown you a lot of non-automated versions that we look at scale because we're trying to look at those computational tools. But in this case, we built a small bridge together with colleagues from TU Munich and Braunschweig, because they had a unique set of complementing skill sets. So we started with a small, as a concept, with a small bridge that I had built in the beginning, which really didn't count as a bridge because it's a 1 by 2 meters, so nobody believes it's a bridge. But we scaled that up to 5 meters. And we also took the opportunity to make that an educational trip. So we put together students from TU Delft and TU Munich and TU Braunschweig, and you'll see them happy and tired after having tried to put this thing together. It's also an experiment in how we get to work with these systems, because in this case, although it's a way smaller project, things didn't go quite as perfect, and you'll see that we needed to react to that on site and with people also learning the system. In this case, we no longer have legs hanging from a scaffold, but we have our robotic legs hanging from a gantry, adding the first layer of the coating. The second one it's a little bit hard to see, but the reinforcement is fiber wound around pins on there. And finally, the last layer of concrete is also added with a robotic process, and a collaborative robotic adding of material and finishing of that structure. This was really taking advantage of our colleagues' facilities, because they're really good in Braunschweig at doing this, and they have a very nice facility for it. So now, because I don't have my laptop in front of me, which is what I would do mostly, and click forward very, very often, I'll click forward a few times and skip over a few projects, because I think it's taking a little bit too long. But I wanted to come back to kind of, let's say, the global prerogative. So what we're trying to do is look at efficient, deployable, flexible formworks. So how we might be efficient in that, not only at the global scale, but at the graded material scale, so really looking at the material. If we are looking at the material, how could we look at hybrid systems or deployable systems? So how could we look at different materials integrated into one? And what does that mean for how we construct things, right? So how are those fabricated in an automated way? This means we need computational design for both the global geometry and the local geometry. We need computational pipelines for fabrication from that design, right? Both in terms of how we might make a textile, but also in how you control that robotic arm to place material where you want it. And we also need to be able to understand what our materials do, because we might have the, let's say, the power or the capacity to make or design whatever materials we want, but that doesn't mean that we know how they behave, and that is one of the big chunks of closing the fabrication-aware design loop. And with that, I would like to go all the way to the end, to the last slide, I guess. I closed it. That didn't help you out, but I'll get them to put it back in. There we go.
We can actually kill the visual for a minute, and I would like to invite Henriette, and thank you very much for Mariana. Please give her a round. I'd like to invite Henriette up as well, and have a brief conversation. I would like to facilitate actually a dialogue between the two of you, preferably. Then just before I open it up for a discussion from the greater audience, we can kill the screen, please, for now. So the title, actually, excuse me, one of the things that's nice about my position in the library and the events like these is that we get two researchers from across campus, all the way across. Of course, you have a pre-existing relationship, but let's say experts that are well, at least working in different faculties and certainly have some differences, but both with expertise in robotics. And so I was wondering if you could just take a minute and respond to each other's work for us, elucidate us, please.
Oh wow, that's a tough one. I think the work is very much well, whether it's complementary or similar or along the same lines. It's definitely within the same field. So we talk about similar things. We might have different tools that we use for that, but we basically talk about similar concepts of being able to control where we place our materials, how do we construct things, where do we construct things, who constructs things, and I think that's our commonality in that sense.
Yes, and I would also add to that of course we work with other experts together. So it's a, let's say, it's a multidisciplinary approach, and I think that we are embracing. Yeah, meaning that we work either with experts from within TU Delft or outside TU Delft, which plays an important role.
Certainly, and speaking of collaboration and these sorts of things, the subtitle for the exhibition is Ecologies of Care. And Mariana, you mentioned the global prerogative. Are these synonymous? And maybe you can maybe comment a little bit about how your work is an act of caring. I think you touched on some of these themes, but yeah, I'm curious. I think your phrase global prerogative was in that direction for me.
That's a very good one. I see, so if you think very strictly of ecologies of care, you might think of something very, very human, but I think of the relationship of how we might, of how we take care of our society to some degree, and in that sense, it's zooming in because I'm not doing really something very specific to humans, but in the way we design our systems, we need to think of what kind of results they might have for that. So if we're thinking of how we build things, we might think of where we build things. So if we're building things in Mexico City or we're building things here, it might look very different. And we might want to think of the human aspect of what our technologies or our proposals have as an implication on day-to-day life. To be very frank, I'd say, okay, should we automate everything? What are the things that we need to automate? What are the tasks that we really want humans to do? And what are the tasks that we want robots to do? Because we'll need both. And there's a little bit of a collaboration there in the work that Henriette shows, that there's always also some collaboration between the two, and they're not in two vacuums.
Yeah. What I could add to that is maybe it's linked very much to also the ladies from the universities of Sydney who invited me actually a year ago to attend the first SHErobots exhibit, and now we had the opportunity to invite them here at TU Delft, and the focus this time is as you mentioned, ecologies of care, and the idea was actually to look at the multi-species approach, meaning that we see the robots as another species. So it's not only about animals, humans, but also about robots and how they coexist together and eventually help each other. So, yeah, I think this is definitely an important aspect. And I do believe that actually the work we are doing, aiming, you mentioned it as well, you showed basically the slide with climate change and basically how we could contribute to, yeah, in a positive manner, reduce the CO2 footprint with these technologies that we are developing.
Great, thank you. And maybe one more, trying to maybe get better each time, hopefully. We're also, the gender of, the title of SHErobots is obviously, mashing up gender with robotics. And so I'm curious, do you see gender having a role in your work, and how do you see that role with coming up with creative solutions and working with hardware and software, perhaps, which are also sort of have these genderized associations, like we mentioned, the big robot arm we have to have out versus sort of the
It's a she.
the she. Okay, the she versus the sort of more invisible work of software and CNC.
You want to say? Yeah, so basically, I can only talk about how I work, basically, and I would like to talk about two different things. On the one hand, the research that we are implementing, education that we are implementing, and the connection between the two, but also the fact that Mariana is perhaps one of the first, let's say, students, female students that engaged easily, let's say, with a topic. But my observation was, and meanwhile is getting better, but at the very beginning there was definitely a majority of male students joining let's say, the courses that we were teaching. So I think it becomes more balanced, which I'm happy to see. And this is also why I think it's important to have you here as an inspiration for the students attending today. But in principle, in terms of how we work, it's a, let's say, it's a combination of bottom-up and top-down, but the students are definitely a driving force, and which I think it's a very enriching experience. Hence, maybe this gives an insight into how we work. I don't know what.
I echo that. I mean, how we work in the end should kind of go beyond the different boxes of gender or how we identify and so on. I very much hope we won't need at some point to call anything SHErobots in hopefully the near future, just so that it's quite implicit that we're all we're all the same and all working, all capable of working in the same creative ways with machines, and that we don't have certain implicit biases towards these things. I like to be a mechanic, but then again, others. I think it goes both ways. So having these kind of implicit biases doesn't help anyone.
Agreed. But it is fascinating how even in sort of subjects like scale, materiality, there are sort of operative gender associations, right? And, and you can see this.
Yeah, as far as I understand, so basically there was a study explaining that equality, let's say, is going to be achieved in maybe the next 200 years. And I was thinking, okay, so it's not going to be in my lifetime. Well,
how many hundreds of years have we been saying that, right?
Yes, but in principle, I can only say, you just, whoever you are, you just need to pursue your goals. And yes, if you do that with perseverance, you're going to achieve those. So hence.
Well, let me open it up to our audience. Do we have any questions related to the research, the robotics, the gender?
Well, this question is for both Henriette, which was my thesis graduation mentor at the TU Delft, so it's great to see you. Thank you, Henriette, for this wonderful lecture. And also for Mariana, it's just what was the beginning of your journey within computational design, robotic fabrication? What was the first inspiration or the first moment that you ever said, I want to dive into this, I want to learn more about this topic?
Maybe I can start with that. So basically my main criticisms towards architecture and building construction has been and still is that the industry is very conservative, and you can see basically that other industries are much more ahead when it comes to these technologies. So I realized that there is a fear, I guess, of getting into these technologies, and my goal was to create an environment where this fear it's less. And so this is why the way we try to teach computational design and robotics is by showing a set of, introducing a set of tools that are quite, let's say, ready-made, prepared very well, so that also students who have no insight can, in relative short time, let's say, at least understand a process that starts with computational design and ends with fabrication. So this is what I can say for me, and Mariana.
For me, it's a little bit. I mean, I don't think I had a moment where I said, I must be this. I think, if I remember it, actually, when I started my bachelor's, we were in the old architecture building, the one that burned down, and back then we didn't have access to some of the master's courses, right? Because we were bachelor students. But I would walk around and I would see these installations that were like active muscles and so on that Henriette and people at Hyperbody back then were doing, and all I could think of was, I want to do that. And this is part of it. And somewhere after the bachelor's, they said, our architecture is boring. It isn't moving. So I joined a multidisciplinary project, and I was the only architect, and was together with a lot of people from across different faculties. And I learned a lot about not wanting to be put in a box, basically, and wanting to have that challenge from different fields. And if you want to have that challenge from different fields, eventually you'll find a common language, and that common language might end up being a computational tool, and it might end up being fabrication, and it might end up being looking at different scales. So it just it just kept going.
Thank you for your answer.
Hello. Yes. Well, thank you both for these presentations. I think that you both showed a lot of very visually interesting and very amazing, visually amazing examples of how your technologies can be used. And I was wondering, is there one of these examples, one of these products that you are working on that you think has the most immediate benefits if we can implement it at a large scale in society right now?
Yes, I happen to believe that what I work on would. If we could, it will take some time. But yes, if we manage to build in a more considerate way and not be wasteful while at it, then I think there's a huge impact to be had there.
Yeah, I mean, if you can point to one of these examples that is like, we should scale this up right now. Like, we need to implement it everywhere right now.
Fabric formwork, well, everywhere, where it makes sense. But fabric formwork.
Yeah, if I can add to that, is that in principle the technologies that we are developing now are partially, let's say, 3D printing is implemented by various companies already in Netherlands and also in the US. So in the US, they managed to construct 3D printed houses for in 24 hours, if I'm not wrong, and for, I don't know, $3,000 or something like that. So they now developed whole neighborhoods in Mexico. So basically, the technology has proven to have a lot of potential. The problems that we still have, it's that cement is let's say, produced with, has a negative environmental impact. So we are looking, for instance, now into cementless concrete, but definitely, and not only that, I explained through the fact that you're structurally optimizing building components, you reduce material use and increase speed of production. So there are various, let's say, contributions that can be implemented tomorrow. And this is also why we work now with Vertical, for instance, together. So we, who are basically actively involved in this research and contribute in collaboration with European Space Agency on this project, also financially.
Right. Thank you.
Thank you for the presentations. It was really interesting. On the topic about the real-world implementation, I also wanted to address this. It's more about my concerns, actually, because I'm also an architect. I'm also in the 3D printing industry. And what I see right now is actually a lot of colleagues are... I do understand that the research needs to go from somewhere and you start with materials that you know, but at the same time, I feel like most of the funding and all the resources and everything is directed in researching how to 3D print cement concrete or how to make decorative elements where this can go beyond just visual appeal of the product or elements 3D printed or fabricated. And also this topic about the materials that is used in digital fabrication is much less, the cost is less and so on, but in practice it's only boutique buildings, they're super expensive. And when do you think, or how do you think we'll go to this future where 3D printing or digital fabrication in architecture is really addressing all these things and it's practical enough? So it's not so expensive and the materials are better than what they are right now.
Basically, what I was saying is that the Icon, the firm in the US, is actually producing houses that are not expensive. So I do believe that the industry needs to embrace these technologies and need to push development, which I have to say it has not been happening for a very long time. So, but now I see it slowly developing. So Vertical is a startup. The big companies, I don't know where they are, but they're not where they're supposed to, in my opinion, humble opinion. So hence, pushing it really to the level of implementation needs industrial partners, and industrial partners who really can leverage what we need to leverage. So basically, of course, we are working mainly on a research level, and actually the industry needs to pick up on that. But it's going to happen, but it's much slower than it should be. And actually, this is also the main criticism also from the European Union and basically the goals for sustainability goals that we have to achieve, that we are architecture and building construction is the least, let's say, progressive, while it's basically, it generates the most waste and has the most negative environmental impact.
What I would like to add to that is that you have, you mentioned cost. Well, any development takes time. You need to compete with, so you have a technology that has a promise, and then that technology needs to compete with something that has had 50 years or 100 years time to develop and perfect and develop skills. So there's a dichotomy there, right? It takes some time to build that up. But the cost might come, why you see it only in boutique something, the cost might come from uncertainty and risk. So by uncertainty and risk, meaning that when we use new materials, we don't know how they behave, so we don't have a code for them, we don't have a way to calculate them, we don't have it, so whoops, this becomes difficult. Somebody's got to take that risk. Somebody's going to be willing to, to do it. Not both in terms of calculating it and signing for it, but in terms of constructing, right? If you take a contractor and you say, okay, look, there's this technology, it's faster, easier, and better, sure, but they haven't used it before, so they'll need some training time. That will be turned into cost. And it takes a while before that reaches the same place as some other things that have had a long time to be trained in. So defaulting to what we know makes sense to some degree, because the shortest path is the known path. But slowly, those things will come together.
So we need more bolder, women-led construction companies that
Sure.
are willing to take that
Yeah.
risk.
Yeah.
It can be anything led.
I just wanted to ask, for example, we talk about how how building industry is a bit behind with regards to digitalization and implementing of these new technologies. And I definitely see that also. Now I'm doing my master and I'm also talking to people, and computational design is also very niche part in the education. Do you have any idea why built environment is struggling with this? Is it the scale?
Well, I have a theory. So basically, of course, and Mariana already started with explaining this. The point is, it's an investment. It's an investment.
But isn't every industry like investing into new technology?
Yes, they do. So, but it's a different mentality, I would say. When it comes to architecture and building construction, only, let's say, if we look at the Faculty of Architecture, in my opinion, it could be much more and more extensive, let's say, the education with respect to these technologies. I think some of the faculties implement this. Meanwhile, more, I think civil engineering and also industrial design. I hope that also architecture is going to pick up this trend, let's say. Let's say I look forward to have a graduation, inter-faculties graduation, for the first time, to my knowledge, in the university, TU Delft, basically on space architecture, but it's going to be combined, so basically 5 faculties are working together, the students are going to work together. So I see there, beginning at least of aligning also with other developments. So I'm hopeful. But you graduate now?
Yeah.
Yeah. So it's yeah.
Well, you can push and find your niche in it as well. If you want it, you can do it. And there's a lot more now than there used to be 10 years ago, for example, even in industry and in what they're looking for. I think one of the reasons the construction sector is so slow in adopting any of these things is because of the sheer scale of the types of projects and the timeline of those projects, right? If we think of product design, you can go from design to product fairly fast. If you think of construction, you won't go from design to product as fast. So by the time you have a building standing there, it's been designed for a very long time, so it's already old news in that sense, right? Because it took a while to construct at that scale, to design at that scale, to deal with all the complexities, because there is a lot, and there are a lot of people that come, not only people, but a lot of different expertise in different companies that come into play. So I think there's an inherent slowness purely because of the nature of the scale of it, right? That doesn't mean, it's not meant as an excuse, but it's meant as it doesn't mean we shouldn't do better. It doesn't mean we shouldn't push further for that value chain. But what you see with most of these projects, and what I can recognize with the projects that we do, is that this works because we represent most of the value chain, right? I'll be the designer, the engineer, the fabricator, the constructor, the everything. But in a real scale, that's all very different stakeholders that come together. So you need to get all of those to move in that direction. And that's not nearly as easy as a smaller scale. So we should do better, but there is an inherent slowness because of the industry's scale in that sense.
I also find it interesting that I think in education I also see a bit of the fear that you mentioned, because I also know about instances when educators discouraged use of computational design, holding on to the traditional approach, I guess. Do you have maybe like ideas why architecture is so holding on to this tradition of designing by hand and not digitally?
We're not the right people to ask.
Yeah. Well, let's put it this way, in the sense that I always say that you should design by hand what you can design by hand, and design with the help of the computer what you cannot design by hand. So I remember that at the beginning there were students engaging in computational design, and they would simulate things that you could sketch. So whatever the shortest path between A and B, it's probably a straight line. So in other words, what I'm trying to say, all these tools are relevant for what they can do for you. But I think that the people who don't use computational tools, it's mainly because they don't know them. So, and then of course you need to, so I can sketch very well, so I'm not afraid of sketching. So, but if I could imagine that if I would be afraid of sketching, that probably I would say, better don't sketch. Computation is the religion, so to say, that you need to adhere to. So, yeah, I think it's probably fear.
But then you would say use computation for what you cannot do by hand, not vice versa. Not use. You said use computation for what you cannot design by hand, but not use computation for use. Sorry, I'm getting confused. But basically, you would say more use hand and only computation when hand is not possible.
No, I don't say that.
I think what we're both trying to say is use the appropriate tool at the appropriate time for the appropriate task.
Yeah.
And that might be sometimes hand sketching, that might sometimes be a computational tool. There's no one or the other, and it might not be either of them also. Just keep an open mind and use it in the smart way.
Yeah.
Thank you.
I think maybe one more, and then we'll wrap it up.
Thank you. I have a lot of questions, but I will choose one. So there was something being said about fear of implementing, fear of using technology, meaning like robotics and maybe more advanced computational design. So I'm really interested in your intuition or how did you understand that there is a fear, or yeah, maybe this is some situations where you saw it.
Yeah, I can talk about this because when I did my PhD, I started imagining that I could program many things, and I ended up realizing that actually what I wanted to program, I couldn't achieve basically the level of complexity that I wanted. At the time, also the tools were much more primitive. And then I went to the computer science, and I worked with the master students from computer science, and then we could together indeed achieve what I wanted to achieve. So basically, I realized that you don't need to be, let's say, a computer scientist to be able to develop things that you want to develop, but you probably need some level of understanding of computational design. So, and this is when I realized that if I would have anticipated the level of difficulty that I was confronted with, probably I wouldn't even have started. So on some level, my naivety was the one who, and my drive to achieve something was playing a role in this. And I could imagine that if you anticipate that it's going to be as difficult, let's say, probably you're going to not engage in that. But probably actually the best...
I didn't say anything.
No, no. Yeah, so, but probably the best is to ask students who just started or who just finished, actually, at some point, engaging in that. I think it's changed a lot, meanwhile, because the tools are much, let's say, more easy to use than they were back then when I started. Yeah.
Okay, I think this has been a great conversation. I'm gonna hold your question. We are, a response? Well, sounds good.
Could the fear have to do with the lack of knowledge or the lack of accessibility within the institution or TU Delft, for example? Because what I'm hearing is that all of these different faculties, they're working on advanced robotics or these manufacturing techniques, but there's like a lack of unity, like for example, a lack of the makerspace or students having access to these kinds of facilities, and that kind of increases the fear or the unknown towards these technologies.
Yeah, I could imagine that you're right. Yeah.
That was it.
Okay. Trying to think of a good segue, but at the point is, we have to conquer our fears together as a community. I don't know, but at the same time, I think the dialogue between female researchers that certainly have had to conquer some fears and some challenges to become where they are today, and then also encouraging some of the student questions here that are also very much everyone being proponent of using robots and CNC and technology for the appropriate things. So let's continue. I think we're going to segue to the more social part of the evening, and we can continue some of these conversations and exchanges. I want to thank you, the audience, for being here. I want to thank my colleagues in the New Media Center for their professional documentation of the event, and I would like to also thank my colleagues in the library for all their contributions to programming and supporting. And I wanted to also point out our next event will be on the 26th of March. We'll be on I believe, the 4th SHErobots Cafe out of 8. And so we'll be back here for lunch. Please join us. We'll be discussing assistive robots and human-robot teams. And I believe this cute robot here on the screen will be joining us too. So I look forward to seeing you then. And once again, we'll adjourn towards the exhibition for refreshments. Thank you very much. And thanks again to our wonderful speakers and inspiring speakers.